The ground stops shaking, and in the settling dust, we see a haunting sight. Modern concrete apartment blocks have collapsed into piles of rubble, floors pancaked, hope lost beneath the weight of their own design. The silence that follows is heavy, broken only by the distant sound of sirens and the crumbling of what once seemed unbreakable. The very material meant to last forever has shattered, its supposed strength now revealed as a fatal flaw. Concrete, so rigid and unyielding, cannot adapt when the earth moves beneath it. Instead of bending, it breaks, its promise of permanence undone in seconds. Yet nearby, centuries-old timber-framed houses still stand. Their walls may lean, plaster cracked and weathered by time, but their wooden skeletons remain remarkably intact. These humble structures, built long before modern engineering, have endured countless quakes. These ancient buildings have survived by flexing and swaying, absorbing the earthquake's energy rather than resisting it. Their frames move with the earth, not against it, allowing them to withstand forces that would destroy more rigid structures. The contrast is stark. Modern strength lies broken, while old wood endures. It's a powerful reminder that progress doesn't always mean improvement, especially when nature is the ultimate test. Why do these so-called primitive structures outlast our engineered marvels? What secret have their builders known for centuries that we seem to have forgotten? The answer isn't brute strength, but a deep understanding of materials and movement, wisdom passed down through generations. These builders respected the unpredictable power of the earth and designed with it in mind. True strength, it turns out, is flexibility. Wood bends, absorbs shock, and returns to shape, while concrete simply cannot. Earthquakes reward the best dancers, not the stiffest fighters. In the dance between earth and structure, those who move with the rhythm survive. These timber buildings, with their interlocking beams and time-tested joinery, have always known the steps to survive nature's violent dance, a lesson written in wood and in survival. We trust that new means better, especially in architecture. Concrete and steel seem invincible, but earthquakes reveal their hidden weakness, rigidity. When the ground shakes, these buildings resist, building up pressure until they snap. In contrast, old timber buildings sway and flex, settling back into place after the tremor. Their resilience isn't luck, but design, born from centuries of experience, not just equations. These structures move with the quake, not against it. Progress isn't always linear. Sometimes the past holds the key to survival. True strength is the ability to move without breaking. Concrete is incredibly strong under compression, making it the go-to material for columns, foundations, and the very bones of our cities. Its ability to withstand massive downward forces is unmatched, which is why we see it everywhere in modern construction. But concrete has a weakness. It's brittle. When stretched, twisted, or pulled apart, it cracks easily. Even small shifts in the ground or temperature changes can cause visible fractures, threatening the integrity of a structure. Earthquakes push buildings side to side, creating powerful forces that concrete alone simply can't handle. These lateral movements test the limits of rigid materials. To help, engineers embed steel rebar inside concrete, giving it some ability to resist tension. But if the bond between steel and concrete fails, the structure can shatter suddenly, leaving little warning. Wood, by contrast, is nature's flexible composite, evolved over millions of years to withstand wind, storms, and shifting earth. Trees bend gracefully in the wind, and timber beams flex during a quake, absorbing shock rather than fighting it. The secret lies in wood's long cellulose fibers, which give it remarkable tensile strength. These fibers allow wood to bend and stretch, distributing stress and preventing sudden breaks. When a timber building sways, it doesn't just survive. It absorbs and dissipates energy, spreading stress throughout the frame and reducing the risk of catastrophic failure. Concrete, on the other hand, resists movement until it can't anymore. then it risks sudden, dramatic collapse. Wood yields, bends, and survives, flexing with the forces of nature rather than fighting against them. The real secret isn't just in the material itself, but in how it's used, how engineers and builders harness its strengths and design for flexibility. In the end, flexibility, not brute force, is the true path to endurance, allowing structures to stand the test of time and the forces of nature. The genius of medieval timber construction lies in its joinery. Instead of rigid metal fasteners, carpenters used mortise and tenon joints, connections with just enough give. A tenon fits into a mortise, secured with a wooden peg, allowing slight movement under stress. During an earthquake, these joints act like knuckles, letting the frame flex and dissipate energy. The friction between wood surfaces converts violent motion into harmless heat. Hundreds of moving joints let the whole structure twist and deform without breaking. Each joint shares the burden, preventing catastrophic failure. The creaks and groans of a timber house in a quake are the sound of survival. This is passive damping at its best, an elegant, ancient solution. The building doesn't just withstand the quake, it dances with it. When a concrete building fails in an earthquake, the result is often pancaking, floors collapsing one atop another in a matter of seconds. The immense weight of each floor compounds as they fall, creating a deadly domino effect that leaves little time for anyone inside to react or escape. The columns, which are primarily designed to support vertical loads, simply aren't built to withstand the intense sideways shaking of an earthquake. When lateral forces hit, these columns can crack, buckle, and ultimately crumble under the pressure. Once a few columns fail, the upper floors lose their support and crash down, crushing everything below in a catastrophic chain reaction. The destruction is often complete, leaving behind only twisted steel and shattered concrete. There's little chance for escape. The collapse is swift and total. Survivors are rare, and rescue efforts become a race against time as emergency workers search desperately for anyone trapped beneath the rubble. The core issue is a lack of redundancy. If even one critical column fails, there's no backup system to redistribute the load. The entire structure is left vulnerable, and a single point of failure can bring down an entire building. Many designs rely solely on columns, making the system brittle by concept, not just material. Without additional supports or reinforcements, these buildings are at the mercy of nature's forces. Soft story designs, open ground floors for parking or shops, are especially vulnerable, concentrating stress where the building is weakest. These open spaces lack the walls and bracing needed to resist earthquake forces. When the quake hits, these weak points give way first, triggering disaster that can bring the entire structure down in moments. It's a design flaw that has cost countless lives, leaving families and communities devastated in the aftermath. Rigidity, without backup or flexibility, is a recipe for catastrophe. True safety comes from designs that anticipate failure and provide multiple paths for forces to travel, ensuring that one weak link doesn't bring everything crashing down. Earthquake-resistant timber designs evolved through centuries of trial and error, shaped by the relentless challenges of nature and human ingenuity. In Japan, pagodas with loosely connected stories and a central pillar sway independently, absorbing shocks and dispersing seismic energy throughout the structure. In Turkey, Humus houses use flexible wooden frames with lightweight infill, reducing collapse risk and allowing the buildings to bend rather than break. Builders learned that heavy, rigid walls were dangerous, flexible frames saved lives, and offered a crucial advantage in earthquake-prone regions. Each disaster taught a lesson, passed down through hands-on practice, not just theory, ensuring wisdom was preserved and improved over generations. These designs treat buildings as dynamic systems, interacting with the moving earth and adapting to its unpredictable forces. Resilience was earned, not invented, tested by the very forces they were built to resist, and proven time and again through survival. As we build for the future, ancient timber structures remind us, true strength is the ability to bend, not just to stand firm. Earthquake-resilient buildings should be repairable, not disposable. Timber houses can be fixed after a quake. Concrete ruins must be rebuilt from scratch. Repairability is a forgotten wisdom in our age of disposable design. We shouldn't abandon modern materials, but we must integrate flexibility, redundancy, and repairability. Mass timber buildings and new damping systems are reviving these old principles. Progress means blending ancient insight with modern technology. The wisdom of the past is as relevant as ever. By learning from history, we can build cities that dance with the earth and survive.